Hello, in these videos, we're going to take a look at examples for finding limits of sequences and determining if they converge. I know the last video with all the different ways we can tell if a sequence converges or not, a lot of information, but now once we have that, we can actually get through limits pretty quickly. So first, one of the first rules we had was if we know how to take the limit of a function, we can take the limit of a sequence. So this first example, I have the sequence 4n plus 10n squared over 7 plus 3n squared. This is just a rational. We know how to do limits of rationals. So the limit as n goes to infinity of 4n plus 10n squared over 7 plus 3n squared. When I have a rational where the degrees match, the limit is the ratio of the leading coefficients. So this limit is 10/3. That means a sub n converges. I'll actually name this sequence for all these problems we're doing. The sequence we're looking at converges to 10/3. Next example is another rational, but this time the degrees don't match. So looking at the limit, when the degrees don't match, we look for where is the degree the largest. The degree is the largest in the numerator, meaning the numerator grows faster. We have a 4 and we have a 3. The numerator grows faster. So this equals infinity. Therefore, n to the 4th plus 3n squared over n cubed plus 1 diverges. The limit does not exist. Next example, sine of 4n pi over 3 plus 12n. We want to look at the limit as n goes to infinity of sine of 4n pi over 3 plus 12n. Because sine is a continuous function, there is no holes in sine, just continues. We can actually pass the limit inside. This is one of the function rules we have. So passing that limit inside the function, we want to look at the limit of 4n pi over 3 plus 12n. What's inside this limit is now a rational where the degrees match. Since the degrees match, we look at the coefficients, which is 4 pi over 12. So this is equal to sine of 4 pi over 12 based on those coefficients on n, which is sine of pi over 3, and sine of pi over 3 is root 3 over 2. So all of our function rules still stay the same. And for this last one that we just did, sine of 4n pi over 3 plus 12n converges to root 3 over 2. For number 4, this is still generally in the function territory, but with this sine squared up top, we know there's some oscillating back and forth happening, and this 3 to the n. How do those work together? Well, we know sine squared, or we know sine n, because sine is never smaller than -1, and it's never bigger than 1, we know that sine n is between -1 and 1. But when I square something, that makes everything positive. So if I square sine, it is never smaller than 0 and never bigger than 1. Divide everything by 3 to the n, and I now have that sine squared n is between 0 and 1 over 3 to the n. Well, the limit as n goes to infinity of 0 is the same as the limit as n goes to infinity of 1 over 3 to the n. 1 over 3 to the n is a geometric with the ratio equaling 1/3. Because the ratio is 1/3, and 1/3 is between -1 and 1, we saw in the last video that the geometric sequence converges to 0. And the limit of 0 is 0. So both of these share the same limit, meaning what is in between has to have the same limit. Therefore, 3 dots, the limit as n goes to infinity of sine squared n over 3 to the n also has to equal 0. So sine squared n over 3 to the n converges to 0. Next example, 4 to the n plus 1 times 7 to the -n. This one requires a bit of rewriting. A negative exponent, when we're looking at the limit, a negative exponent drops that base to a denominator. So limit as n goes to infinity of 4 to the n plus 1 all over 7 to the n. 4 to the n plus 1 means 4 times 4 to the n, because we can add exponents together. So last rewrite, this 4, because it doesn't have any n's, can be pulled out front. And we're looking at the limit as n goes to infinity of 4/7 to the n. This is, once again, a geometric sequence. 4/7 to the n is geosequence with r equal to 4/7, and 4/7 is between -1 and 1. So this limit comes out to be 0, meaning the sequence 4 to the n plus 1, 7 to the -n converges to 0. Next example, we have -1 to the n over 4 to the n times n to the 3/2. -1 to the n is just changing things between -1 and 1. Sometimes the fraction is negative, sometimes it's positive. That means -1 to the n is either 1 or it's -1. So it's between those two values. Dividing everything by 4 to the times n to the 3/2, we have our sequence sit right between -1 over 4n to the 3/2 and 1 over 4n to the 3 halves. Both of these are functions we already know how to take the limits of. The degree of the denominator is bigger, meaning the limit as n goes to infinity of -1 over 4n to the 3 halves is also equal to the same limit n goes to infinity of +1 over 4n to the 3 halves. And the denominator is growing while the numerator stays the same. Both of these are 0. Therefore, the limit as n goes to infinity of -1 to the n for n to the 3 halves is also 0 by the squeeze theorem, just like in problem 4. Therefore, -1 to the n over 4n to the 3 halves converges to 0. Few more examples. Example 7. We have 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. There's no rule I can write. However, for limits, it's all my values have to be getting really close to the limit. So all the values have to get close to the limit. Because these ones are popping up every so often, ultimately, even if I have a million zeros in a row, eventually there will still be a 1, and so we're bouncing between values, meaning this sequence diverges. So if suddenly you're bouncing away from the limit, then the sequence will diverge. Example number 8 is here to remind us of a limit rule we know, but might have forgotten. We know for functions, and if it works for functions, it works for sequences. The limit as x goes to infinity of x plus a over x to the x equals e to the a. We can prove this using L'Hopital's rule. I'm not going to walk through that here, but we know this for a fact. So if I switch all these x's out for a's, or n's, I should say, we have the same exact form. So the limit as n goes to infinity, n plus 2 over n all to the n is equal to e squared. Therefore, the sequence n plus 2 over n all to the n equals, it converges to e squared. 9 and 10 are growth rate problems. There's a whole long list that I encourage you to review regularly, but in general, the list we need to know is that natural log grows slower than polynomials, which grow slower than exponentials, which grow slower than factorials, and that grows slower than n to the n. That is the main list we really need. So looking at this list, the natural log of n grows slower than n squared. And since the natural log of n grows slower than n squared, the limit as n goes to infinity of the natural log of n over n squared will be 0. So that sequence, ln n over n squared, converges to 0. Same thing on 10, n factorial is faster than any number to the n. Here is any number to the n, here is n factorial. N factorial grows faster. Doesn't matter that the base is 99. The base could be 1,027,000. The fact that we're comparing against n factorial means that n factorial is growing faster. So limit n goes to infinity of n factorial over 99 to the n equals infinity by growth rates. So the sequence n factorial over 99 to the n diverges. And our last example is taking this idea of growth rates and our function ideas and combining them together. When you first were learning limits of functions and learned the rational rules of look at the degrees, you would divide by the largest power in the denominator. Well, when we take growth rates, we can do the same thing. We can divide by the largest thing in the denominator. So limit as n goes to infinity of 9 to the n plus 7 to the n all over n to the 1000th plus 9 to the n. Using our growth rates, the item that grows the fastest here is the 9 to the n. It's the exponential with the largest base. The n to the 1000th, again, doesn't matter that it's 1,000, it's still a polynomial, so it grows slower than an exponential. So we're going to divide everything by this 9 to the n. So that's the fastest growing in the denominator. So limit n goes to infinity of everything divided by 9 to the n, 9 to the n over 9 to the n, plus 7 to the n over 9 to the n, all over n to the 1000th over 9 to the n, plus 9 to the n over 9 to the n. Here we have two things that are dividing by themselves. Something divided by itself is 1. Here, the 7 to the n over 9 to the n, that is 7/9 to the n. It's a geometric. We know the limit of a geometric when the ratio is between -1 and 1. So -1 is less than 7/9, which is less than 1. Geometric sequence limit is 0. And then the last one, this is growth rates. An exponential grows faster than a polynomial, so by growth rates, this last ratio limit is 0. So in the numerator, we have 1 plus 0, which is 1. And in the denominator, we have 0 plus 1, which is 1. Therefore, the whole limit is 1. This means our sequence, 9 to the n plus 7 to the n, all over n to the 1000th plus 9 to the n, converges to 1. And there are all the examples. Once we have all those rules, the limits go really quickly. And in the last video, I will show some terminology we can use for sequences.